When a liquid is kept in a closed vessel, part of the liquid evaporates and the space above the liquid is occupied by the vapors of itself. These vapors exert pressure on the layer of the liquid and on the walls of the container. This is known as vapor pressure of the liquid. What happens to this vapor pressure when a non-volatile solute is mixed in it? What is Raoult's law? Is it a special case of Henry's law? What is an ideal solution? What is the nature of the plot of an ideal solution? Can we achieve ideal solution in practicality? Let us explore these concepts. Our discussion starts with the topic vapor pressure. What is vapor pressure? Pressures on account of the vapor of the liquid. So vapor pressure is the pressure exerted by the vapor or the gas of a liquid, that means vapor state of a liquid, when it is in dynamic equilibrium with its liquid phase at a given temperature in a closed system. What does it mean? It means that if we have a system which is a closed system where the vapors are unable to escape and we have a liquid kept in that container which is a closed system, the vapors are unable to escape, then at above the surface of the liquid there are vapors existing of the same liquid that we have taken. If I have taken liquid A in the container, then the vapors will be of liquid A itself. And if it is a closed system, then this rate of vaporization and the rate of condensation will be same and the system will be in dynamic equilibrium. Now, factors affecting the vapor pressure of a liquid are temperature. Of course, if I increase the temperature, the kinetic energy of the liquid molecules escapes. It increases, the kinetic energy increases and more of the liquid molecules will escape. So this is a system first system which I have talked about to explain the vapor pressure. Now, if I increase the temperature of the liquid, the vapors that will be obtained will be more on account of greater kinetic energy of the liquid particles. More and more vapors will be obtained and I will say the vapor pressure increases. So vapor pressure increases with temperature. Next is nature of the liquid. Of course, when I am heating, I am telling more and more vapors are obtained of the liquid in the vapor phase or in the gas phase. Now, if I don't heat also, maybe I am not heating it only, yet I have vapors of the liquid above the surface, above its own surface. Now that depends on what type of interaction is present between the molecules, between the particles of the liquid itself. If the interactions are weak interaction, then the vapor, if this interaction is a weak interaction, then the vapor pressure ought to increase. For weaker interaction, for that reason, acetone and alcohol, see liquids with weak intermolecular forces, they have high vapor pressure, because their intermolecular forces are weak. But strong intermolecular forces exist between H2O molecules and they have lower vapor pressure. Okay, so the vapor pressure is lower. That means it is difficult to obtain the vapors of that liquid, but that doesn't mean that I will not get the vapors of the liquid. I will get, but the vapor pressure will be less if the interaction is strong. The third factor is presence of non-volatile solute. That is the Raoult's law that we will discuss again. That means that to the liquid, I am assuming that every liquid has some sort of volatility. The volatility can be more if the interaction between the liquid particles is weak, and the volatility is less if the interaction between the liquid particles is stronger interaction. Now, when I add non-volatile solute to the liquid, then the solute particles that occupy the surface of the liquid will cause less of the liquid particles to escape in the vapor phase, and hence the vapor pressure is lowered. And it is dependent on how much of the solute particles are getting added. Next, surface area only in open system, of course, because in a closed system, the liquid and its vapor phase will be in dynamic equilibrium. The equilibrium will be set up if it is a closed system. As I have said that the rate of vaporization and the rate of condensation will attain, it will be same, and the system will attain a dynamic equilibrium after some time. But in an open system, if the surface area is more, then the rate of vaporization will increase. So these are the factors, the four important factors that affect the vapor pressure of the liquid. Now, vapor pressure of liquid-liquid solution. I have taken two liquids, say A and A dash. They are two liquids. Or I say A and B. Both are in liquid phase. B generally we use for solute and A we use for solvent. So here I am considering a case where the solute is also liquid, the solvent is also liquid. So two or more liquids when they are mixed, then the total vapor pressure will actually be on account of volatility of each of the liquid components. And then I can say that it is affected by the individual vapor pressure of the components and in what proportion they are mixed. In an ideal solution, the interactions between molecules of different components are similar. What does that mean? It again means that the interaction that exists between the solvent particles, the interaction that exists between the solute particles, and the interaction that exists between the solute and solvent particles are almost equivalent interactions. But in a non-ideal solution, a solution which is non-ideal, obviously this condition is not actually happening. The AA interaction is not equivalent to BB interaction, is not equivalent to AB interaction. That's why it is a non-ideal solution. Now the question arises, if the interactions are same, if the solution is ideal, what will happen? What does it actually mean? What happens to an ideal solution? For that, we need to see Raoult's law, which describes how the vapor pressure of an ideal solution is related to the mole fraction of its components. For any binary solution, I started the discussion, the introduction part of my video by telling binary solution, which is in our syllabus. Binary solution means a solution containing two components only. And if I talk about liquid-liquid solution, that means the two components are in the liquid phase. So this part, vapor pressure of liquid-liquid solution, for that we will see the Raoult's law. For solutions of volatile liquid, that means assuming that A and B both are volatile in nature. As per Raoult's law, we can say that for a solution of volatile liquid, partial pressure of each component of the solution is directly proportional to its mole fraction. Why we are talking about partial pressure? Because the vapor pressure has contribution of both A and B. So the pressure that is exerted by A can be considered as PA, and the pressure that is exerted by B can be considered as PB, and they are the partial pressures on account of the contribution of the volatile component A and volatile component B respectively. So we can say that partial pressure of A is proportional to the mole fraction of A. Partial pressure of B is proportional to the mole fraction of B as per Raoult's law. And For that we can say PA is equal to PA naught into XA, PB is equal to PB naught into XB, where PA naught and PB naught, they are the proportionality constant for the expression, but it has some significance. What is the significance? They are the vapor pressure of pure components A and B respectively. That means that if I have only component A, then what pressure will that component A exert? It will exert PA naught. If I have only component B, it will exert PB naught. And if I have A plus B, then the partial pressure of A will be PA, the partial pressure of B will be PB, and as much of volatile component A I have, that much of partial pressure is exerted. So PA is proportional to XA, PB is proportional to XB. And these are the individual expressions for PA and PB as per Raoult's law. Now, from Dalton's law of partial pressure, this P is actually the P total, the total vapor pressure is actually having the contributions of both A and B. So I can say the summation of the partial pressures of A and B is equal to the total vapor pressure as per Dalton's law of partial pressure. And from Raoult's law, this is from Raoult's law, we can say that PA, since PA is equal to PA naught into XA, we are just substituting the values and we are getting this expression. Now, XA plus XB is equal to 1 because it's a binary solution and we have only two components, A and B. It makes up the entire solution. So, mole fraction of A plus mole fraction of B is equal to unity. And in place of XA, we can write 1 minus XB. So, in case of XB, we can write 1 minus XA. Substituting for XA by 1 minus XB, we get the expression with respect to XB. So, P total is equal to PA naught plus PB naught minus PA naught into XB. By simplifying the equation, doesn't it look as Y is equal to M into X plus C? Where if I can plot P total versus XB, I will get a particular plot whose Y-intercept is PA naught. So later on we'll see that. Now the question arises, what is the composition of the vapor phase in equilibrium? So the composition of the vapor phase in equilibrium with the solution can be determined from the partial pressure of the two components. If in the vapor phase, the composition, the mole fraction of A is Ya and of B is Yb. Again, I am showing the same reference diagram. That is, if A, the mole fraction in the solution is Xa and mole fraction in the solution of B is Xb, then in the vapor phase, the mole fraction of the vapor of A is Ya and mole fraction of the vapors of B is Yb, then we can say that Pa is equal to Ya into P total. That is, the partial pressure of A is equal to mole fraction of A in the vapor phase into the total vapor pressure. Similarly, partial pressure of B is equal to the mole fraction of B in the vapor phase into the total pressure. So, any component I can have its partial pressure equal to the composition or the mole fraction in the vapor phase into the total pressure. That's a general equation. Now, can we say Raoult's law is a special case of Henry's law? Yes. Why? Let us understand. In the solution of gas and liquid that we have seen in Henry's law, gas and liquid, if we consider that one of the component is so volatile that it exists as a gas, then it can be said that Raoult's law becomes a special case of Henry's law, in which Kh becomes equal to Pa naught. We are considering here that P is equal to, or let me show it here only, that PA is equal to PA naught into XA. And as per Henry's law, the partial pressure was proportional to the mole fraction. And so if I say for A is equal to then KH into XA, now it seems that if I talk about the gas to be so volatile, then it is compared to Raoult's law, and Raoult's law can be compared to Henry's law. That means gases are more volatile. Of course, they will escape to they'll remain in their own phase only. Vapors will be more. Now, out of the two liquids in Raoult's law, A and B, if the volatility is so much so that can be compared to a gas phase, then we can say Raoult's law is a special case of Henry's law. That means you have to say that out of the two liquids A and B, for a solution where you are actually explaining Raoult's law, if the component have so much volatility that it almost exists as a gas phase, it exists as a gas, then we can say that Raoult's law becomes a special case of Henry's law. Then you can compare PA naught to KH and they will be almost the same. Next, vapor pressure of solutions of solid in liquid. We were talking about two liquid solution. Now we have to talk about a non-volatile solute and a volatile solvent. That means a vapor pressure that you will be getting, that will be on account of the solvent itself, because the solute is non-volatile. Now, don't you think that if I add a non-volatile solute, there will be a lowering of the vapor pressure? As I said that the non-volatile solute will be occupying the surface of this thing, the surface of the liquid, and so less solvent particles will go to the vapor phase. So there is a net lowering of the vapor pressure on account of the non-volatile solute that is getting added. Since we know mathematically from Dalton's law of partial pressure that P is equal to PA plus PB, and PB, that is a partial pressure, we can ignore, we can actually consider it to be negligible because B is non-volatile. So the vapors that will be obtained above the liquid will be on account of the liquid solvent itself and not on account of the solute, which is non-volatile. So we can say P is equal to PA naught into XA. And since XA plus XB is equal to unity, in place of XA, 1 minus XB is written. So we can just simplify the expression and we can get this, which is relative lowering of vapor pressure, which is equal to mole fraction of the solute. When we will be discussing colligative properties, we will be seeing this as the first colligative property. Now, why it is relative lowering? See, the expression is PA naught into XB is equal to PA naught minus P. So, simply we are just bringing PA naught to this side and we get what? PA naught minus P by PA naught is equal to XB. That's how we have got it mathematically by simplification. But since PA naught minus P is the lowering of vapor pressure, PA naught was the vapor pressure of the pure component A. On account of adding the non-volatile solute B, the pressure has lowered and has become P. So how much lowering? This is known as lowering of vapor pressure. So PA naught minus P is the lowering of vapor pressure. And relative lowering is PA naught minus P upon PA naught. Why? Because in relation to the pure vapor pressure, that means vapor pressure of the pure solvent A, how much lowering has taken place? That is known as relative lowering. So PA naught minus P by PA naught is the relative lowering, which is equal to the mole fraction of the solute. We can see over here. There will be various calculations related to this, substituting the value of mole fraction as because we know mole fraction of B can be considered as NB upon Na plus NB, that is total number of moles of A and B. Next, ideal and non-ideal solution. I was telling that what is ideal solution? What happens if a solution is ideal? Let us understand what happens if a solution is ideal. If a solution is ideal, first and foremost thing is this. The forces of interaction that exist between the AB, solute to solvent, is equivalent to the forces of interaction that exist between the solvent particles AA and solute particles BB. And for this reason only, this is the core reason for which a solution behaves as ideal. And what happens if it behaves as ideal? It obeys Raoult's law over a wide range of concentration at a specified temperature. Raoult's law will be obeyed if a solution is ideal. And if Raoult's law is obeyed, what does it mean? It means the total vapor pressure P will be equal to the summation of the individual partial pressures of the components. So, P is equal to PA plus PB. And PA was proportional to XA and PB was proportional to XB, for which it is equal to PA naught XA plus PB naught XB. So the nature of the plot is somewhat like this, which I said for a single component. Just see, assuming left hand side has no I'll say solute particles, and you are gradually adding the solute. So right hand side, what is happening, you are considering solely the vapor pressure is on account of the solute particles, because B we have considered to be solute. So PB naught is the vapor pressure of pure component B and PA naught is the vapor pressure of pure component A. In this plot, we can see that the vapor pressure of PB naught is at a higher value. Okay, that means the volatility is greater, has been assumed. So this is the total vapor pressure, which is equal to PA plus PB, summation of the partial pressures of A and B. And as per Raoult's law, the dotted plots, they are the individual plots for the Raoult's law for each component. What happens at this point of intersection then? Why do they intersect? Here we can see there is a mole fraction. Here we can see that XA is 1 and here XA is 0. Here XB is 0, here XB is 1. So when will it intersect? It means when it intersects, the point of intersection of the two plot, it actually depicts the mole fraction of one component is equal to the mole fraction of the other component is equal to half. XA equal to XB is equal to half, or X1 is equal to X2 is equal to half at the point of intersection of the two plots. Such examples where AA, AB and BB interactions are equivalent, are similar, are these examples which I have given. Methanol, ethanol, see similar type of interaction, similar type of compounds. N-hexane, N-heptane, benzene, toluene, these are all the examples. Try to explore as many possible examples you people can. Now, reason for ideality, I have told you the first reason, and the solution of A and B liquids will be ideal if A and B have similar structure and polarity. If they have similar structure and polarity, then only the interactions will be similar. And that is the main reason. See, when I talk about methanol, ethanol, both are alcohol. Not much difference in their molecular mass. N-hexane, N-heptane, both are alkanes. Not much difference in their molecular mass. So structure polarity should be equivalent, should be similar. Then only it will obey Raoult's law, then only the forces of interaction will be similar. So for an ideal solution, since it obeys Raoult's law, this is the expression that will be got. Delta H mix, that is, there will be no enthalpy change after mixing A with B. There will be no volume change, neither decrease nor increase when you are mixing A and B. For an ideal solution, these are the conditions and these are the reason. So these are the conditions of ideality, these are the conditions of ideality, and these are the reasons of ideality. And if ideality occurs, what happens? It will follow Raoult's law. Here that we have seen over a wide range of concentration at a specified temperature, and this is the plot for ideality, ideal solution. Now, non-ideal means will not obey Raoult's law for all concentration. If it is not obeying Raoult's law, that means P total is not equal to PA plus PB, and PA is not equal to P naught A into XA, and PB is not equal to P naught B into XB. Delta H mix is not equal to 0 and delta V mix is not equal to 0. Not equal to can be two things, either greater than or less than. If I am telling it is not equal to 0, that means it can be less than 0 or it can be more than 0. That's why not equal to 0. Now a non-ideal solution, it can show deviation means two types of deviations. Either a positive deviation from Raoult's law or a negative deviation from Raoult's law. Positive deviation means what? What does it means? That the partial pressure of each component and the resultant total pressure are greater than the pressure expected on the basis of Raoult's law. The vapor pressure increases. The vapor pressure increases. Why? Because AB interaction is weak. If AB interaction is weaker than AA and BB interaction, then only you will obtain more of the vapors. Then only the vapor pressure will increase. If the solvent to solute interaction is weaker, then only more of the vapors you will get and the vapor pressure will increase, and it will show a positive deviation. The vapor pressure of the solution will be higher. Now, what are the characteristics of a positive deviation? For Raoult's law, PA was equal to PA naught into XA. For a positive deviation, PA will be greater than PA naught into XA, PB will be greater than PB naught into XB. Similarly, delta H mix will be greater than 0, that is positive. And when I say delta H mix is positive, that means endothermic. If it is negative, means exothermic. So delta V mix is greater than 0. That means positive. The volume will increase when you have added A and B, and the volume has to increase. A plus B, the volume will increase. Why will the volume increase? Because the forces of interaction between A, B is weak interaction. So the volume increases. Now, such examples are ethyl alcohol and water, acetone and CS2, carbon disulfide. So they are the positive deviations. See the nature of the plot. This dotted lines are for ideal solution. Everywhere you are seeing a hump. A hump means the vapor pressure has increased. Everywhere the vapor pressure has increased. So next is negative deviation, which is just opposite to that of positive deviation. Negative deviation means the vapor pressure of the resultant solution is less than expected from Raoult's law. And if the vapor pressure is less, that means AB interaction is a stronger interaction than AA and BB, or I can say solute to solvent interaction is a stronger interaction between the interaction that is existing between the solvent particles and the solute particles. So PA is less than PA naught into XA, PB is less than PB naught into XB, delta H mix is less than 0, delta V mix is less than 0. So delta H mix is less than 0 means negative, and that means the reaction or the mixing is exothermic in nature. Heat is liberated. Delta V mix is less than 0 means volume has decreased. There is a decrease in the volume. There is a decrease in the volume. Why the volume decreases? Because the interactions are stronger, the particles are held closer. So there is a little bit of contraction in the volume that is taking place in the level. So here are the examples of solutions that are showing negative deviation from Raoult's law. Nature of the plot also we have seen. There is a dip. There is a dip in the vapor pressure in each case. So this is a tabular form of ideal solution, the factors, and non-ideal, positive and negative deviation. Always remember that people confuse here in the forces of attraction, because positive deviation they always remember as everything is greater. Delta H mix is greater than 0, delta V mix is greater than 0. But please keep in mind, why is it greater? Because the vapor pressure has increased. Why is the vapor pressure increasing? Because the interaction between the solute and the solvent particles is weaker, and so more number of vapors you are getting for positive deviation, which is just the other case in negative deviation. Next, coming to azeotropic mixture, they are binary mixtures having same composition in the liquid and the vapor phase at a constant temperature. It boils at a constant temperature. See, if I take two liquids or two substances A and B, obviously A and B will have different boiling temperatures. The liquids will have a different boiling temperature, but their temperature at which they boil is constant for an azeotropic mixture. And remember that the composition in the liquid phase and the vapor phase is same for an azeotropic mixture. We have two types of azeotropic mixture. One is minimum boiling azeotrop. That means the temperature at which A plus B boils is less than either of the two temperatures. If A boils at a temperature say X degree, B boils at a temperature Y degree, A plus B will be lesser than X and Y. So we can see that their boiling point is less than either of the two components, or it can be lesser than any of them. So it shows, since it is the boiling temperature is less, means they boil easily. If they boil easily, that means more and more vapors are obtained. Since more and more vapors are obtained, they show large positive deviation from Raoult's law. So minimum boiling azeotrops show large positive deviation from Raoult's law. And at a particular concentration, at a particular composition, so 94.5% ethyl alcohol mixed with 4.5% water by volume can produce a minimum boiling azeotrop. Maximum boiling azeotrop, again they are a binary solution whose boiling point is more than either of the two components. So what will happen? If the boiling point is more, that means it takes time to boil, and if it takes time to boil means the vapor pressure decreases, and so it shows large negative deviation from Raoult's law. And of course at a specific composition, so this is an example, HNO3 and H2O at a particular composition by mass, it is forming maximum boiling azeotrop. So this is something which I have kept as a notes. What is azeotropic mixture? Same thing that I have discussed. What are the types, examples, and this is a board question which is rarely asked but asked. Why fractional distillation fails? It's a very good question. Why can't you separate the components of an azeotropic mixture by fractional distillation? What happens in fractional distillation? Separation of components occurs by fractional distillation when they have differences in boiling point. Now A and B, which is forming azeotropic mixture, before formation of the azeotropic mixture they have different boiling point, but at a particular composition when they form azeotropic mixture they boil at the same temperature. So their entities are not different now. They behave as one entity. for which you cannot separate them. So the vapor cannot be separated by fractionating column. So what is happening? The vapors has the same composition as the liquid at the azeotropic point. So you cannot separate them by this method because they have uniform composition in the vapor phase and the liquid phase, because they boil at a constant temperature. So this is what I have highlighted. Now the question arises, if anyone asks you that then how can we separate? If we are unable to separate by fractional distillation, what are the methods, techniques of separation? Though the techniques are not there in the NCERT, yet you need to know certain things. Like there is a method which is known as azeotropic distillation. That is, I can mix a third substance to break the azeotrop, and once I break the azeotrop, I can definitely separate the mixture. And other methods are pressure swing distillation, membrane separation, extractive distillation. So these are the methods by which you can separate an azeotropic mixture, but do keep in mind, why can't you separate the azeotropic mixture by fractional distillation method? I hope this content is quite understood. If not, please go back, listen to it again and again, and in the comment section drop your query, which will be attended by me. I hope we have got answers to the questions like what is Raoult's law? What is the effect of mixing non-volatile solute to the vapor pressure of the solvent? What is the mathematical expression of Raoult's law? How the plot looks like for an ideal solution? What are the conditions of ideality? And what are the conditions for non-ideal behavior of solutions? If we got answers to these, then I think the learning outcome has been achieved by all of you.